basically like a mini piano. Uh, so uh, if we go to our schematic, I can explain it. So over here we have our power supply. There's a 9-volt battery holder. And then I created like a little pad so that when I'm constructing the PCB, I can put one of the ends of the probes of my multimeter on the ground, and then the other one on signal, and other places where I change the voltages and put it through some components, just so I can check that everything's in place. This is just a 2 by 2 millimeter pad. Um, so it goes from our battery to a switch, and if the switch is in the 2-3 position, it's an open circuit, and electricity doesn't flow. These are just our filtering and our bypass capacitors. And then here's our 5-volt regulator, and I made sure to make this a low dropout regulator. The difference between other regulators is that they dissipate a lot of the energy in terms of heat, and it makes the system really hot. And the other big difference is that you need a very large voltage difference between your input and your output. So, but with a low dropout regulator, it only needs to be different by like 0.2 volts, for example, like with this part MCP1702 that I found on DigiKey. So after it goes through our capacitors, this is just an LED I added to make sure everything's working in the system. This is a 330 ohm resistor onto an LED. So if this LED turns on, I know that power is flowing to the system. So this powers the whole system. So over here, VCC of the clock, which is another 555 timer, is connected to the V plus pin of the clock, which is pin 8. Threshold trigger. This is put in astable mode. So over here we can see that the resistance A is fixed, and resistance B of our input to the DIS pin, or the pin 7, changes. So these the resistance values here change, and this one stays stable. So basically what I'm trying to do is I'm trying to change the frequency based on which momentary switch I press. So if I press switch 1, then R2 and R14 go into this frequency equation over here. And this frequency basically determines the frequency of the sound. So this, I think, I based it on like chromatic scales, so 12 notes on the piano in the middle, I think. And then once that goes into the input, our output pin, which is our audio signal, goes into an NPN transistor, which in this case is a current amplifier. And by amplifying the current, you also amplify the volume. And finally, it goes into a speaker, and you can hear the sound. So each button creates a different frequency, and that gets amplified by the NPN transistor and then creates a sound through the speaker. Of course, all happening through the output of our clock, which is our 555 timer. So if we go to our PCB now, over here, and we go into 2D, the 2D mode, here you can see our battery and our power supply, our 5-volt regulator goes into the timer. And like with my other PCB, I ground plated the top and bottom planes, and then just added VCC and other signal lines through the rest of it. And I made sure to make the signal lines, for example, this is, I think, VCC, which is why it's very thick. I decided to make them thicker than the other copper connections that just connect one pin to the other. And I just made sure that the overlay over here, like it kind of matched the piano keys. So here's our like white keys, and then in the middle is our black. And yeah, this is our diatonic scale. So this is like C4 sharp, I think. And here's our speaker, which I added just an overlay for, so I can place it on. So if we go into our 3D view, there's our battery holder, our resistors and our switches that go into the clock that determine the frequency, and then the output of our clock goes into the NPN transistor, and then goes into the speaker, which I'll put over here after connecting to the positive and negative leads right here. So yeah, that's my design of a mini piano using a